Just a few more seconds. All right, we can start. Good afternoon and good morning to everybody. Today we see Vlatko Vedral's QISS seminar. The format of the seminars is like a 30 to 40-minute presentation followed by ample Q&A. So if you have a short clarifying question, just unmute yourself and ask it. Otherwise, let's keep like more difficult questions for the question session. And Vlatko, so the stage is yours.
Thank you. Thank you, Andrea. It's a pleasure to be talking to you, and I'm grateful to be invited to speak about this topic. It's going to be very informal, and as you said, I don't have too many slides. Maybe some of them are technical, and it might require a few more discussions, if you like, depending really which angle you come from to this issue. So this is really, let me give you an overall motivation for this, which is very broadly speaking to revisit how we understand static interactions. So I'm actually extremely happy, incidentally, that our collaboration has been renewed. I think it's fantastic to have funding dedicated to purely fundamental issues. I think most of you will know where I come from, and I always get disappointed when I see too much applied stuff and focus on, you know, things like machine learning and all of that stuff. I think it's good to have a bigger focus on fundamental physics. It's something that we really shouldn't lose, and I think we should up the incentives to investigate things of this kind. Certainly technologically, we're getting close to being able to test lots of these things, and that's going to be my point. Now, here I have, let me motivate my talk through a beautiful, this is a great book. It's by Panofsky and Phillips. It's basic classical electricity and magnetism. I think it's probably the best book on this topic. And I'm literally gonna read out to you the two initial sentences, chapter 1, page 1 of Panofsky and Phillips. Okay, that's how they start. It's really a brilliant book, much better than Jackson in my view. It's an amazing combo of kind of tight, mathematically rigorous formulation, as well as lots of physical insight. And here is what they say, chapter 1, page 1. The interaction between material bodies can be described either by formulating the action at the distance between the interacting bodies, or by separating the interaction process into the production of a field by one system and the action of the field on another system. These two alternative descriptions are physically indistinguishable in the static case. Are they? That's the point. The whole point of my talk is to really try to stick my neck out and say they're not. They're actually different. They're physically different. They don't just tell you a different story. They certainly tell you a different story. But I think if that was all there was to this thing, it would be maybe interesting to a philosopher of physics, but it wouldn't be interested that much maybe to a physicist. So it would be a bit like different interpretations of quantum mechanics, unless really they're distinguishable, which means they are probably not interpretations. Then somehow a physicist doesn't really know what to do with these things. Anyhow, the trick I'm going to be using is the trick that all of us are familiar with in quantum information. And that, I think, is why this escapes the notice of various people, for instance, coming from quantum field theory, because I think they are simply not used to these kind of maneuvers. So we're kind of adding extra moves to the moves that they usually consider. And so the standard trick is really that whatever you call a global phase, this is true for anything. The phase arising due to anything, any kind of symmetry. You swap indistinguishable particles, you get a phase. You usually hear it's a global phase, it's undetectable. But every global phase can be converted into a local phase. by simply making a superposition, doing whatever you want to do in one part of the superposition, keeping the other one as a reference, and then interfering these two. That converts every global phase into a local phase, and then you can see what that produces and what kind of effects that has. And the other fundamental aspect of quantum mechanics is what we call local tomography. Any correlation in, let's say, entangled systems could be completely accessed by doing measurements on each of these subsystems locally. Of course, at the end of this, you need classical communication. I'm just gonna wait maybe for that's very good. It wasn't, I think, me producing the echo. So basically, any state can be estimated through these local quantum actions, if you like, and then, of course, exchanging the classical information about these actions, and that can, as we all know, estimate any correlations in the state. So let me give you a little bit of a story about these things. And what I really want to say is that the covariant formulation, even of static interactions, is not only closer to the spirit of what we believe are fundamental principles in physics, but somehow, like I said, one feels that it can even be discriminated from other formulations. So I'm kind of dangerously going in this direction of trying to say that not all gauges are the same, and somehow quantum mechanically, at least, there could be a way of telling them apart. And I think, to me, that's an interesting topic to think about. Of course, it impinges on all sorts of other discussions that we've been having. I'll be talking about the electromagnetic field, but as we all know, there is a lot of excitement about the gravitational field, and all of these questions somehow can also be asked of other fields, and the story will be very similar. So, as you know, the principles that we really adhere to very strongly, and I think most of us would be extremely reluctant to give them up, is obviously the relativistic Lorentz covariance. So that's something that not only makes sense theoretically from various angles, but of course has never really been violated experimentally. There is this locality of interaction, which is also an extremely, of course, that's been challenged too. Each of these has been challenged in physics, but I think we believe that these principles have been upheld so far. Locality of interaction literally means that by acting on one subsystem, you cannot really change properties. I'm just speaking very generically now of another subsystem. When it comes to quantum field theory, and here we are talking about QED really, the way that this gets implemented is to couple different subsystems. So J, of course, is the current operator, or in this case, just current. I'm writing it classically or quantumly. It doesn't really make any difference. It's just a coupling at exactly the same point. So the current at the point X can only affect immediately the vector potential at that same point. And you can see that it already captures the Lorentz covariance as well, because I'm even writing it as a product of 4 vectors. So this is usually what every field, I think this is all really well known. And of course, the third principle that we add to this is this gauge invariance. And if you derive the action from this, you can show under some very, again, general conditions that actually this interaction is also leads to a gauge invariant, if you like, formulation. So I want to elaborate a little bit on these things, and then I want to present to you, I think, what Chiara and I had in mind. I think Andrea asked me to talk about our recent paper on detecting ghosts. I think I'm giving you a slightly different, because I think either you've read the paper or you might be tempted to read the paper. There's no point really in repeating exactly how the argument is done there. I think it's nicer to give you a slightly different picture, maybe, that makes it more interesting. But basically, the message is more or less the same. So the approach that I like best out of all of these, and I think it encapsulates the spirit of what I've talked about so far, is due to Lawrence. And this is the other Lawrence, the older Lawrence, the Danish Lawrence. Not the, for a long time, these two Lawrences were confused. But the Lawrence approach, the Danish Lawrence, the Lawrence without the T, if you like, there's no T in his surname, actually had an alternative theory. There's a great book by Whitaker, if you're interested in the history of all of these things. Anyhow, Lawrence wrote down an alternative, in a way, to Maxwell's equations. And I think he used this logic that, of course, we also use in our modern formulations, which is to start with the source here. J, again, is the full current vector, if you like, and then propagate this. D is the retarded propagator, if you like. It doesn't really matter what this function looks like, and I think most of you know what it looks like. But it's just a very causal approach, in the sense that we take all of these things right from the start. We don't write it in another formulation that may or may not be equivalent, but somehow it doesn't contain the essence of this from the start. So this really is my favorite way to do it, and I think it lends itself very nicely to quantization. Start with the classical equations of motion, put hats on whatever you think are the relevant entities to quantize, and of course this is subject to arguments and tests and so on. And then you preserve exactly the form. You don't really have to modify anything if you do it this way. Anyhow, you have the source current. It propagates, if you like, at the speed of light, causally to point x prime, from x to x prime, and you are simply then computing the vector potential at that point. So this already includes what we said, the principle of locality, if you like, as well. It's obviously Lorentz covariant, the other Lorentz covariant, if you like. These names are a bit confusing here. But what is interesting, of course, as well, is that if you only leave it at that, you won't get Maxwell's equations, actually. If you only start with this inhomogeneous field equation here, you know, the wave equation for A and the source J on the other side, you will not get only the Maxwell's equations, if you like. You will get something more general. And then if you now, on top of that, introduce charge conservation, again, a principle we strongly believe in, and most of you will know it's intimately linked to somehow gauge invariance as well, depending which assumptions you made from the beginning. But if you assume the charge conservation, you can see from this equation immediately that what comes out is a very similarly looking analogous equation for the vector potential. So this is like some kind of conservation of the vector potential. But what it really is what we call the Lorentz gauge. And you can see that this is relativistically covariant as well. The whole approach is like that. So if you have this equation up there and you have the Lorentz gauge condition, you are equivalent to Maxwell's electrodynamics. It's the same formulation. But like I said, I like it this way, simply because we are starting, this is how Heisenberg presumably would have done. And some field theorists like to do quantum field theory this way, because I set the classical equations. And now, like I said, I have to upgrade J and I have to upgrade A, presumably, to operators. So now it's a causally linked equation for the sources that we think of now as quantum operators and the fields that they create, which we also think of as quantum operators. But everything else is the same. And in fact, the methods which we use to solve these kind of things are remarkably similar, of course, classically and quantum.
You take a short question?
Of course.
If you, sorry, if this is a long discussion, yeah, if this is a long, no, can you close everything yours and just use this? Okay. Okay. Now you have to close everything.
I'm sorry.
Okay. Oh, hope this works. Sorry. The short question is this: I understand you get solutions of the Maxwell equations, but you don't get all solutions of the Maxwell equation. Is that correct? For instance, suppose J equals 0, the Maxwell equation has a huge number of solutions. You don't get any of these.
Oh, I see what you mean for the free fields.
No. Also, if it's not free, I mean, given a J fixed, there are other solutions than the ones in your equations for all.
Yes, yes, I think you're right. This in a way embodies the spirit that you are really directly connecting the potentials with the sources. In a sense, there are no potentials without the sources. That's kind of what this gauge fixing does for you.
So, for instance, in cosmology, there are photons before being charges. You kill all that cosmology. Is that right?
Yeah, that's a good question. I haven't thought about. I think this is a very good point. Whether how far this could be pushed. I think that's a very good point, Carl. Yeah. Thank you.
Sorry for that.
No, not at all. It's an excellent point. In fact, it won't be relevant for what I have to say because I have very simple lab-based, of course, experiments. But you are right that certainly in the early universe, these things could actually be decoupled. So let me just all of this is so far classical, and of course the difficulty, and that's what I want to make a transition into. But just to justify this word ghost that we use, is that if you look at this Lorentz condition, which here is written in position, if you like, if you go to K-space, then of course you've got this very simple equation K mu A mu equals 0, which is the usual way that we use to justify that only the transverse components are really relevant, dynamically speaking. So this in a way could naturally get you into saying, well, maybe I should acknowledge from the get-go that these other modes, the longitudinal and the temporal, the scalar, are not really, or they don't need to be quantized. Let's put it that way. Whereas the other approach, and these are the two extremes, obviously, there are all other gauges in between these two extremes, so to speak. The other one would be to say, well, we should quantize them all. They seem to be present in this kind of formulation at the same time. But what we then must be able to do is implement this Lorentz gauge condition. We have to discuss what that really means quantum mechanically. And this is, of course, one of those things that is still debated. And I think from the maybe even 50s onwards. Certainly not a completely settled issue as far as I can tell. So, of course, the famous...
Sorry, can I ask a quick question?
Of course.
There's some background noise, so let me know. I'll shut up if it's too much. But isn't the usual quantization setup that we do quantize them all, and then we discover that some of them have negative norms, so they don't make physical sense, there's no probabilistic interpretation for them, and then then we realize that because of gauge invariance, they're not physical, so that's not a problem?
That's a very nice point, and actually thanks for bringing it up, because I won't be going into these technical issues. You're right that in some approaches if you just quantize it straightforwardly while maintaining the Lorentz covariance, you will end up with a temporal mode having negative norms or negative probabilities, as you said. And this is an issue. And there are many ways in which people argue how this could be accommodated. You can even ignore that, incidentally. I think there will be possibly a slide where I can comment on that. You can even ignore that issue, and I think that's what you suggested as well. Simply compute your amplitudes in all of these 4 modes, and then through imposing, as you said, the Lorentz gauge condition, you will actually realize that somehow the longitudinal and the scalar, the temporal modes, cancel each other out, because one has a positive probability, the other one has an equal but negative probability. So that's one way of thinking about it. And I think the way you put it is that it almost sounds very fortuitous. We are very lucky that when we get a mathematical issue of this kind, it seems not to matter, really. It doesn't really affect anything. That's one way of talking about this. And again, this is something I want to challenge. Can we actually detect things?
Okay, but just to make sure, we also agree that if you don't remove them, then the resulting amplitude you're computing will not satisfy unitarity requirements.
Yes, you have to worry about how to convert. You're right. So that's part of the technicality. You have to. These are operators that are not Hermitian for these modes, if they come out straight from this kind of direct covariant quantization. And if you exponentiate them to get the dynamics, they will not be unitary. So there are all sorts of tricks how to convert this kind of thing into a unitary evolution. It's doable. You can make transformations so that you convert these skew-Hermitian into Hermitian operators, and you can then exponentiate them to get standard unitary evolution. That's possible too. I hope that answers at least partly the question.
Yes, thank you.
Excellent. There's a huge amount of literature on this, and I'm really grateful that you're raising these points as we go along, because I won't be able to mention them. So here is this famous Gupta-Bloiler method of imposing the Lorentz gauge condition. So if you just blindly put a hat, upgrade the A field into a quantum operator, which is what we always do, then you get this funny looking equation that an operator equals 0. And no one really knows what this means. You know, is this like a matrix with all the 0 entries? In fact, this somehow doesn't really make sense. It's very difficult to interpret something like this. I think you can, in some ways, you can even try to interpret this, but I don't think anyone reached anything really interesting in that direction. And what they suggested instead is to actually say that the physical states are the states which, when multiplied by this, give you a 0 eigenvalue. So basically, rather than taking an equation operator equals 0, which mathematically is difficult to see what that really means, you simply take a state psi. And again, I'm just jumping through a few steps. All of this is standard stuff. You get really an equation which says the longitudinal, these are the annihilation operators in K-space, the longitudinal minus the temporal, acting on that state equals 0. So these are your physical states, as people call them. These are the states that satisfy your Lorentz condition throughout. You have to, of course, impose this throughout your dynamics. And again, I think exactly as you were asking, this is a condition that seems to suggest that somehow the temporal and the longitudinal modes really cancel out. So, you know, one trivial state which satisfies this is, of course, the vacuum state for both of these modes, or coherent state of the same amplitude in both of these modes, or a state 0, 1 plus 1, 0, which is an entangled state between these modes. So there is a whole subset of states.
I would say that every physical state needs to satisfy this property, not just some.
That's
right?
the statement. You should never, your evolution should never take you out, according to this logic, of this subspace. That's kind of what's done. And then, of course, I'm then raising this question that if really the two modes cancel out, in a sense, they have an equal but opposite effect in whatever we do, then, you know, are they observable? Maybe we really don't need to go through all of these trouble. Maybe it looks nice aesthetically that it's Lorentz covariant, but we might as well just use the Coulomb gauge. Leave these two modes. Leave the interaction, the static interaction, as C numbers, if you like. It's a non-local part of the Hamiltonian, and then just simply quantize the transverse modes. And that's I think what I'm saying on this slide. I think it's a current, if you like, J0 is the density at x, density times density at x prime, and then divided by the distance, the usual Coulomb interaction that we all know. But of course, the dissatisfaction with this is that this interaction looks non-local. It really acts at a distance, and that's the whole point of introducing the concept of the field, as I read from the Panofsky book in the first sentence. The whole point is that you want the charge to make some kind of dent in the field locally. You want this to propagate to the other charge, as we saw in the Lorentz formulation, and then you want the other charge to simply pick up this disturbance of the field. And I think that seems to me like a better description of what's going on, which is why I somehow prefer this this gauge. I want to, before I now do this main bit really about static interactions, what I want to say is that, of course, this doesn't violate causality, the Coulomb gauge. So that's always what we come back to say, well, it looks non-local, but it's, micro-causality is still fine. It's just the story is very funny, because when you move one of these charges a certain distance further away from the other charge, this part of the Hamiltonian will automatically assume this new distance. In that sense, it will be non-local. It sounds like you are doing something at the distance which you ought not to be able to do according to the principle of locality. But the story in the Coulomb gauge is that there is now part of your transverse wave that gets generated that cancels that extra non-local bit out. So it's very interesting how these two non-local parts conspire in this formulation to give you a perfectly causal description. So don't get me wrong, we are not obviously violating, and this everyone knows this, we're not violating causality, but somehow the picture makes you a little bit uneasy there that there is something non-local. But my point is not going to be just that it's not in the spirit of this. My point is that classicalizing these things, claiming that the longitudinal and the temporal mode of the electromagnetic field are C numbers, ought to have observable consequences. And that's always the case. If you take a system and you treat part of it classically and the other part quantumly, you're going to run into some kind of trouble. It's going to be inconsistent. We know that if one system is quantum and it couples to another system, then this other system has got to inherit fully this quantumness. Most of our discussions when it comes to gravity are of this kind as well, actually. So that's all I wanted to say about it. There's a lot more to be said. Now, how does Lorentz view this static? And again, it's exactly the story that Panofsky and Phillips tell us. And of course, that's why Faraday introduced the concept of fields, and Maxwell formalized it and all of that. I think everyone understands the need for that. So you have this nice looking equation where the density really at x through this retarded causal propagator really affects the vector potential, the temporal vector potential as an operator in this picture at point x prime, and then the charge, the other charge that may be sitting at x prime, will through the local interaction with A0 at x prime pick that up. And that's kind of how we understand the static interactions here. I want to just make a few comments that certain things are extremely unhelpful in this picture. And I think they keep, because historically we got stuck in certain language kind of issues that are really not helpful here. And I think if you're encountering some of these problems, you will probably come across things that may not make sense to you. And I think the reason for that is that they really don't make any sense. And I just want to tell, so part of the language here, what people go into is virtual particles. And so basically people say one charge emits a virtual. Why virtual? Because we already concluded that these modes, the temporal mode, cannot have disturbances that are the same as free propagating photons in the transverse modes. There are disturbances, they are coherent states actually. That's what kind of disturbance you get. But you cannot create states that behave like free propagating photons in these modes. That's why people say, but let's assume that they are virtual photons somehow, negative energy or whatever language they use here. And I just want to alert you to the fact that this is the same as how we talk about tunneling, for instance. It's just the language is very misleading. It doesn't reflect what's going on, but maybe it gives you some intuition, but it really is a wrong intuition. So you will remember that when you have tunneling, we also have a very similar story that we tell. We have a particle that's coming from the left of the potential. And then when the particle goes through the potential, tunnels through the potential, we end up talking about a particle of negative energy, of imaginary momentum, if you like, that somehow goes through this and then ends. And then people say, but don't worry, it's okay that it's borrowed this energy because it still does it within the time that doesn't violate uncertainty. All sorts of nonsense statements are actually written about all of this, and it's simply not how this goes. That's not the story here, which is that you never need to talk about particles of negative energy. What you're describing really is the perturbation series where you are using these negative norms and negative energies, but that's not really what's going on there. You're describing a bit of mathematics. I want to give you another picture which is maybe closer to this. The question is now, how should I understand that? And as I said, if you have an electron at the position X, what it generates through this kind of coupling, obviously, is simply a coherent state. So when you put a free field is just a bunch of simple harmonic oscillators, as you know. When you put a charge there, you basically drive each of these harmonic oscillators. You kick it from the vacuum into the coherent state of amplitude alpha, whose amplitude, of course, depends exactly on the strength of this interaction here. But you can see that the exponential of this operator that we keep talking about, which is the density times A plus A dagger in these modes, is actually going to result in a coherent state. So then one picture of these static interactions is to have two particles, each of which has created this kind of coherent state disturbance in its own vicinity. And the question, again, some people at this point say, and one of these photons now tunnels from one of these charges into another, photon with a negative energy and all of that. But I think you don't need that language. In fact, that's not really how this ought to be understood. And the analogy is the same. all of these things are the same. Once you understand quantum mechanics, you will understand that every interaction is the same as every other interaction. So the same thing happens when we talk about atoms bonding into molecules. So, you know, we have two atoms and we have an electron that can sit close to one atom or the other atom. And then you can see that even the name for this bond, the resonating valence bond, is implying that now this electron is hopping between two atoms. It's kind of tunneling between the two atoms and so on. But this is not really what's happening at all. The electron is not doing anything of that kind. What happens, of course, is that these atoms, when they are closer, they couple more strongly. And your new eigenstates are, of course, not the same as the old eigenstates. And if you use the old eigenstates, then obviously they will change in time with respect to this new interaction Hamiltonian. And everybody knows this. So what happens really when you bring two atoms together is that you gradually end up going into a different joint eigenstate. The electron ends up there. And if you diagonalize this 2 by 2, you know, the energies is initially just the electron being next to one atom and the other. And now when they have an interaction V, when you go into the new basis, you will realize that 0 minus 1 state, which means the electron is here minus here, is of course a state with lower energy. And that's really all there is to chemical bonding. All chemical bonds are really of this kind, and nothing is resonating, nothing is tunneling, no electron is hopping through classically not allowed things. That doesn't make sense. Actually, you don't need to say that. And the same picture now, if you translate what I just said, and I said it with atoms because again, it's something that we all know. If you say it with photons and charges, your charges are now like your nuclei of the atoms, your photons are now like the electron. And if you do exactly the same calculation with the Hamiltonian, you will get the famous on-site energies. You will get the off-diagonal elements as the charges approach one another. And when you diagonalize this Hamiltonian, you will get new energy levels. And you can see that the new energy level will contain this term, which looks like the Coulomb term. And that's exactly how quantum mechanics explains this. So basically, you go into an energetically more favorable state, the ground state, and your ground state now is exactly displaced by what we call the Coulomb potential. That's all there is to it. And you can follow this in time as it happens, and you don't have to imagine. Nothing virtual goes anywhere, really. It's just a misleading language in this case. So what I want to do now is really last few minutes tell you about why I think this is interesting. So the claim I want to make is that this explanation of interactions is certainly favorable, even in the static case, simply because it gives you this local account of how the disturbance is created locally, how it then causally propagates, and then how it's picked up locally at another place. It's just everything we understand in physics behaves exactly this way. We have no reason to step outside of any of these kind of assumptions. So I'm going to somehow claim that it's real and that it's quantum, not just classical. And I want to tell you that there is a way of somehow testing this. That to me sounds very interesting. And it somehow it goes against this dogma that all gauges are somehow physically equivalent. And so I just want to clarify, when I say that something is real, I know that we discuss many of these things with philosophers of physics. And I mean real in the stupidest possible simpleton quantum physicist language. I mean it's as real as anything else you would say it's real. So if you tell me that an atom emitting a photon as it decays, and another, this is the famous Fermi kind of problem, and another atom getting excited by picking up this photon, if you tell me that this is a proof of the existence of transverse photons, that they are real, then that's what I want to say. I have an experimental piece of evidence that other modes are as real as transverse modes. That's what I mean. There's no other mystical meaning to reality at all. I'm just being completely simple-minded in this case. So I'm saying the way that we detect photons in general, flying photons, free photons, is also by coupling it somehow to charge and then measuring the current response of this charge. And that's all I'm doing here. I'm not doing anything else. By quantum, now I really mean that if you have a charge in a superposition of states, then your mode, your temporal mode, will also have to be simultaneously excited in both of these places. Just like Schrodinger's cat. Like I said, if you put a charge in a superposition, it's got to have a superposition-like effect. It's got to entangle to the field locally. And this is interesting. And why is this interesting? Because the Coulomb gauge says that these guys are not quantum. They don't exist according to Coulomb gauge. How can I entangle to something that does not exist? That's actually a very simple question. And that's it. That's all there is really to what I want to say. Let me elaborate a bit more. So the experiment really that we want to do is just one of those very simple. There is just one subtlety that I want to emphasize. It's really just one subtlety there. So it's a very simple experiment where you have a reference electron. Let's say it could be any charge. I just call them electrons because it's the simplest thing to do. And you have another electron which is in a superposition of two different locations. So that guy, the electron 2, will be interfering. But it will be interfering in a field somehow, joint field that's created also with what I call this as a reference electron, which could be localized in one position. It doesn't really matter. That guy doesn't really have to be in a superposition of states. So this is different to our usual discussions of gravity, because in gravity, we want to assume much less than what I'm assuming here. Here, I'm assuming the full QED. I'm not trying to rule out all other classical descriptions. I'm already buying J.A interaction. All I'm now asking is, do all 4 components of the vector potential matter, and can they be detected in some way? That's actually a specific question I'm asking. And of course, you will know that this interference here will pick up the usual phase difference, which is simply the difference between Coulomb energies, because here they are separated by one distance, x1 minus x2, and then x3 minus x1 in the other. It's the usual phase that we all know. And in fact, what I'm presenting to you is how we do control knot with ions as qubits. So this is already standard part. Of course, no one worries about locality and causality here, but it's a standard part of all of this. So what does this mean if you were to pick up in the Lorentz gauge? This phase is exactly a function of the degrees of freedom of this temporal gauge. So that's one way of saying the temporal, the scalar gauge affects things, and in particular, it affects the superposition of this charge, which can be detected through interference. And that's kind of what I mean by real. It has a real effect on a charge. Now, what I want to say is, why hasn't this been picked up? And I have a guess to make here, and that's kind of what I want to conclude with. And I will conclude with an explanation. Why haven't people noticed that there is an entanglement between the charge and the scalar part of the electromagnetic field, even in the static case when the charge is in a superposed state? And my answer is something that I like to call fake entanglement, which is the following one. Almost invariably, all of our experiments that we've done so far, and this is where quantum information comes in handy because it challenges, it broadens our perspective. All our experiments so far are take a charge, which in this picture has this coherent state cloud, if you like, of scalar field around it. Then you make a superposition of this charge, and it's at this point that the charge becomes entangled to the electromagnetic field. But if you want to interfere this to get the phase, as I was advocating in the previous slide, you will have to bring these two branches together at the end to make the interference experiment. You will have to close the loop. I'm saying you will have to. You don't have to. That's the whole point. But when we do these experiments normally, we end up opening the loop, creating the superposition, and then closing the loop. And when you close the loop, these two coherent states, which have a certainly less than one overlap with one another, they're really entangled to the charge, now are brought back together, and they are no longer entangled with the position of the charge. So the charge acts in this kind of experiment literally as though there was no scalar potential present there, even though the phase of the charge, like I said, will be a full function of this. So now the question that I want to ask, and you can compute this amount of entanglement, and probably if I just ask you to guess on the spot what this entanglement is actually, I'm looking at the overlap between a coherent state of the field, scalar mode, created at two different locations that are distance r apart. To a zeroth order approximation, you would say this is probably something like e to the minus fine structure constant. There are all sorts of intuitive arguments I could give you why the fine structure constant actually should feature. Obviously, it's the coupling strength between the charge and the field. And then there are these log corrections. It's multiplied by the log of the distance between the charges divided by some distance. Of course, you know, if you let these distances go to zero, you will get all sorts of divergences. You need to make some cutoffs, and there are some reasonable guesses for this distance. But I think in most of these situations, this doesn't really matter where you take that. And so what I'm saying is that the amount of entanglement is there, but if you look at it, it's actually very small. It's e to the minus alpha, and alpha is 1 over 137. So it's a very small number. It's a number close to zero, which means that the overlap between coherent states is almost unity. It's actually not that easy to detect. And the question I have is really, can we detect that? So that's what I think. If we could detect this entanglement, which would be a reduction in the visibility of the interference, but it couldn't happen if you close the loop. You would have to actually make a superposition of the charge, then do local measurements. And that's where I said this local tomography starts to matter. And you would have to estimate the correlations between these two positions without closing the loop. And that's in principle doable. It's an even harder experiment, if you like, but it's in principle doable. And according to this logic, that should actually give you not just the angle itself, but also this reduction in the visibility. And of course, the larger the distance, the larger the reduction, although remember, it goes logarithmically, so it doesn't really grow that fast. However, the point I'm making is maybe it's hard to measure exactly and confirm this with the present technology, but in principle, it is a possible experiment. And I claim that this experiment really cannot give you the same result in the Coulomb gauge, because in the Coulomb gauge, not only are these modes not quantized, but the Coulomb gauge would say they are unphysical. They don't even exist, actually. And I think that's an interesting thing. So I'm gonna put these conclusions up, and I'm gonna stop my my talk here, and I'm happy to have a few discussions if we have time. So basically, static interactions, according to this logic, if you follow the principles that I mentioned, also require us to introduce all four modes of the electromagnetic field. You need to quantize them as well, because as soon as you have a superposition of sources, then the field must inherit this kind of superposition, you know, the Schrodinger cat kind of experiment. Now, I don't want to speculate, because I really have no idea what the origin of this is and what the conclusions are. But one can kind of always say, well, if you claim that the gauges are really different and they have different consequences, then what does this really mean? Why is this like that? Are the Maxwell equations to be corrected? Should we trust more the Lorentz approach? Is it to do with the non-zero mass of the photon, whatever? I actually have no idea, but I think it would be really interesting, first of all, just to do this experiment, to prove whether or not there is this kind of entanglement that would exist in this kind of picture. And of course, the last point I want to make is that you can make the exact same analogous argument for the linear regime of quantum gravity, and you would again talk about the reality of modes that in some gauges we would not consider real. Thank you very much for your attention. I will stop here.
Thank you, Vlatko. Let's all thank Vlatko Vedral for the talk. I'm sure it was it already started stimulating a discussion. So so the floor is open for questions. If you can raise your hand via the interface of Zoom, and then I'll call you out. So Carlo already raised his hand.
Go. Yeah, hi, Vlatko.
Hi.
Thank you very much. So this is super interesting. I want to make a comment. I have to reflect about what you're doing and to digest it. So the comment I'm making, I'm not really sure about. Please take it with a first reaction that might be wrong. So while you were talking, I think I was agreeing to everything except one phrase. So I just want to get to that.
Of course.
I was agreeing with what you were saying about the possibility of describing things in the way you do, and also in this very nice sort of physical, concrete picture.
Yes,
you're doing. I think it's convincing. It's very convincing. The only point where I said, wait, what is Vlatko saying? Is the moment in which you say, and therefore, in other gauges, we're not going to get the same thing, and therefore it's going to be different. Now, allow me to just make a one-line advertise of the paper I did with Flaminia and with Li Qing, in which we worked in the temporal gauge, in the A0 = 0 gauge, in a field basis.
Yes.
And it seems that the picture we're getting is like yours. I mean, there is explicitly this sort of cloud that you can have.
Yes.
And we could talk about it seemed to me, I mean, I might be wrong. We could talk about the same kind of entanglement that you talk about.
Yes.
So if you are polemical against the position that says, the longitudinal zero mode don't exist, and I agree with you. But if you're making a point here by saying only in this gauge this picture comes out, I'm not sure.
I think, Carlo, that's a great point, actually, because I think I only looked at these two extreme gauges, but you are absolutely right. I think that what I'm saying, at least in this experiment, could be done, because remember, in this picture, when you are satisfying the Lorentz condition, your longitudinal and temporal gauge behave identically, if you like. So in that sense, you could say, why don't you just flip the two? And I think that's what you are describing. Why don't you just actually take one of them to be 0 and just acknowledge the reality of the other one? And it seems to me I think this would also comply with the experiment I have in mind. You're absolutely right. I don't need two ghost modes at all for what I'm saying. So I think you're right. I will have a look at that at your paper, but I think it's correct conclusion. Whether we could come up, now I'm thinking, actually you got me thinking about an experiment that would maybe probe both of these at the same time, because you're right, there will be a range of gauges that satisfy this logic. And there will be other gauges that clearly don't satisfy the logic because these modes are simply classical or even non-existent. It's a good point. I don't think the experiment I presented does not discriminate between the two.
Yeah. Okay. So we're close.
I think we're in perfect agreement. Yes.
Yeah. So this is this closing comment of mine. I think it's somehow one thing is to accept the fact that the same physics can be described in different languages, so to say.
Yes. Yes.
A different thing, which I believe is a mistake that people we disagreed with, you and I both disagreed with, are making, is to take a language and make a metaphysics out of it and derive things which come not from the choice, but from making a metaphysics out of language. And so I think that's there are alternative. They're the same physical phenomena all the way through, including correlation and entanglement, that can be described in different manners.
Yes.
And the last thing we should do is to disagree about language issues.
I agree. I agree.
That's just,
I agree. Exactly the danger. The danger is, as you pointed out, if you take some of these languages too seriously, and you really then extrapolate the consequences.
Exactly.
This will lead you astray. I think. I agree.
Exactly. This means misunderstanding.
I agree. And it's remarkable how much of our language obviously is still classical, right? Because our intuition is presumably, evolutionary speaking, still classical. So even this, I gave this simple tunneling example because even there we mix this. We want to have a plane wave, but at the same time we want to talk about a particle that tunnels through this. Already that is incoherent. Quantum mechanics simply doesn't allow both of these at the same time. But I think we kind of happily describe this because it gives the right result. And I agree, if we extrapolate this and take this too seriously, then probably that's a wrong thing to do.
Thanks.
Yeah. Thank you.
And there is Chatu.
Yeah. Hi, Vlatko.
Hi.
Carlos' question inspired me to ask you this question, that the experiment that you're proposing with Chiara, it's to test the reality of the scalar field, right?
Yes.
So of
or
the scalar
as Carlos said now, it could be any of these two extra modes, because probably you can rotate between them and still preserve this.
Yeah, that was my question, that if you could think of a different experiment to test the longitudinal part, or if you have some thoughts in mind, because I know that in the paper you restrict everything to the scalar component, right?
Yes, because
therefore
the phase we get is Lorentz gauge. That's it. It's all scalar.
Yeah, exactly. It's all scalar, but but I don't know if that is a defect of fixing the Lorentz gauge precisely, and you could get the same component but with the longitudinal.
I have a feeling exactly what Carlos said, that if you did it in the temporal gauge, you would get the longitudinal to do that work for you. And I think because in this experiment we are only really thinking about estimating one number, if you like, the reduction in the visibility, then I don't think this experiment can discriminate between these two. I think that's a very good point. But I do think there must be experiments that would somehow try to engage both of the modes. That would be interesting. I haven't thought about that.
Also, the requirement of Lorentz invariance, could be put in the experimental setting somehow, so that you further restrict some gauges that are not Lorentz covariant. I don't know if that makes sense.
Yes, I think, lots of these reminds us of all of these discussions with hidden variables, right? Local hidden variables and Bell inequalities, and the way you're trying to rule out certain propagations between the two parties. I think this is all similar in that. So some of these extra C numbers that we introduce do look like hidden variables to me, right? Of certain kind that you're introducing to make up. I think you're right. You could test it. I think maybe the difficulty would be really to create a very large superposition over a big distance. With the charge, it seems to me this is really difficult technologically. So somehow your local measurements may not be fast enough with respect to this, but that's the only comment I have.
Thank you.
Yeah.
Hey, hi, Vlatko. Thank you for a very, really interesting talk.
Thank you.
So I have two questions. The one question first maybe is simple, but I just didn't get your point that since there are the longitudinal mode and the temporal mode, and if they cancel, wouldn't they cancel in the experiments that you propose?
No, that's the interesting thing, that in this gauge, that's a very good point as well. In this gauge, somehow you are really working with a coherent, that's again related, I think, to this question. You're working in a coherent state being present in the scalar, in the temporal mode, but being zero in the longitudinal mode. And if you write these physically allowed states, they will be of this form. So you have to update the Lorentz condition when the charge is present. And that's actually not difficult to see, because I think all you need to do is take the condition I wrote down and evolve it unitarily, do kind of a Heisenberg evolution of this operator equation. And when you do that, when you update it, you will see that the charge density now features in this new constraint. And that's interesting. So I think it's a very good point that in this gauge, somehow this asymmetry between these two ghost modes is preserved. However, like I said, if you do change the gauge, right, then probably you can actually do it the other way around.
Yeah, thanks a lot. So I will read the paper more carefully. And the other question is it possible to do some Higgs mechanism so that couples to scalar field and have, since the massive vector is much better understood, so having a limit of Higgs mechanism may be helpful?
This is a very interesting question. I haven't thought about it at all, and you are right that this is all about entanglements, if you like, with this extra Higgs field. In some sense, the mechanism is very similar, right? Because through this entanglement, you actually make something that's necessarily massless due to gauge symmetry, in fact, into a massive thing that kind of breaks this symmetry. I haven't thought about that. So could you detect that amount of entanglement? That sounds fascinating. I don't know. Actually, I know very little about high energy experiments at that level. You know, what kind of resolution they have, but I think it's really worth investigating this. I'd be very interested in talking about it more.
Yeah, so I'm actually a theorist, so I tend to think about it in theory, but nevertheless, so I can check that how experiments can be done.
It would be great to see whether any of these experiments are at that level. I think that sounds very exciting. It's a great suggestion.
Yeah, thank you.
Thank you.
And Simone Speziale asked a couple of questions in the chat because he's in the train and it's a bit too noisy. So I will read them out one at a time.
Please.
So the first one is, I was thinking about an experiment to prove that temporal and longitudinal components are not physical. So I have sunglasses and they are polarized. How do they work? I can compute explicitly the amount of electromagnetic radiation that comes off from a paddle, bouncing off of a paddle, in terms of the two physical polarizations predicted by Maxwell's theory. If the other two components had physical effects, it would show up in this calculation and the way it compared with experiments. No need of fancy experiments. Do you agree?
This is, do I understand correctly that this is completely within classical physics? This is classical electrodynamics you're describing.
It sounds like this.
Then completely agree. There's no problem there. I think the problem arises, as always, when you have the sources which are in superpositions. The two key ingredients for all of us is really, and I understand that field theorists never think like that. They have some kind of input states, which are eigenstates of the free field. They have some, minus infinity to plus infinity, and they never think about anything remotely close to what I was describing. So I do believe that you can probably in classical optics maintain this view without any problems.
I see, this is very interesting. This story of quantum sort of revealing.
Yes, that this becomes a quantum issue, I think. Yes. Sorry, but there was another question you mentioned.
See, there was a second question.
Yeah.
So here is what is it called? The Gupta-Bloyer method.
Yeah, that's it. That's it.
Okay, it does not break at all the consistent QM treatment of the EM field, as you seem to imply at some point. But maybe I misunderstood. In the Gupta-Bloyer method, you impose only the holomorphic part of the gauge condition, treat it as a second-class constraint, and use the results found by Dirac a long time ago. Of course, I agree, as this is Simone, that is a mathematical procedure and one needs physical tests of it. Don't take me wrong, but I think in the specific case of electromagnetism, we have plenty and there is not much left to discuss.
That again I think again this is a question of testing it in a really highly quantum mechanical domain. So if you do ordinary scattering experiments, if you do ordinary interference, you could ask, for instance, why don't we see this in our atomic spectra? I can do some kind of superposition of electron at two different energy levels. My answer is that you always end up finishing the interference by closing the loop. You always bring these two possibilities, the two separate spatial states back to the same state. So I think if you think about any of these simple experiments that we've done so far, none of them utilize this local tomography. That's why I would say none of them can be a counterexample to this. But again, obviously, I'm not aware of all the experiments that have ever been done. But it seems to me this just doesn't occur to either spectroscopists or high energy physicists or field theorists. They just don't think about these things.
Yeah, that's a very interesting point. Obviously, echoing the BMB experiments. I actually have a question about this.
Of course, go ahead.
I will take my chance as a chair. It's about this tomography experiment.
Yes.
So I think it's a great idea, doesn't to do an interference experiment without recombining the particles. But to my understanding, to do state tomography, you need to measure a lot of the different observables, right, of the system. And my doubt here would be, is there some kind of snatch where to measure one of these, you actually have to bring the particles back in position?
Excellent question. It's an excellent, Andrea, this is a very deep question, basically, because it keeps popping up in all of these related experiments that we want to do. So I think your question is, if I think of these locations as qubits, in a sense that in each location, either I have the vacuum or I have one electron, which I would call my Z basis. So there is Z basis for the A location and there is Z basis for the B location. What I need to measure for this, to confirm this, it's only one type of correlation, and it's, for instance, XX. So I need to go into the complementary basis, and I need to measure X on A and X on B. And when I do it over an ensemble, of course, the expected value will give me exactly the phase as well as the amplitude, if you like, of my interference. And you are very right now. How do I actually, and so this is an issue that always comes up in these discussions of the mode entanglement. How do I achieve this measurement in the X? How do I rotate locally from Z to X? So the only way I know how to do that is to bring some kind of reference. So without closing the loop, of course, as you said, if you close the loop, you've overcome this problem. There's no issue. But if you want to do it locally without closing the loop, you really do need another system as a reference. Then I know how to do it, but I don't know any other way of performing this. So I think it's a very important point that you brought up. I didn't want to discuss it initially, just not to make the talk infinitely long and not to distract us from the main point. But I think this is a very important point in an actual experiment. How easily can we really do this? And I think your concern would be, is this then equivalent to closing the loop?
Well, No, I wasn't thinking that far, actually. I was
It
wondering if you are forced to. Yeah, it could be. But what do you mean by bringing another system as a reference? You mean having another system in superposition nearby?
Yes. And I think this is simply because of these super selection rules that apply to fermions, that you cannot really make a superposition of even and odd states, if you like. So, you know, if my Z basis is the presence or absence of a fermion, then my X basis is a superposition of the vacuum and one fermion. And that's something that you cannot really prepare. Or at least there are good reasons why this is super selected. Let me put it that way. I mean, whenever we say something cannot be done, we are usually proven wrong in the future. So I don't want to be too dogmatic about it. But let's say there are some principles that people believe may prohibit us from that. And so what I really need is another similar reference system. It could be of a different type, but I think it helps here that it's really another electron, let's say, if I'm talking about an electron. And then I can work in the subspaces which conserve the number of electrons locally, rather than having to think about what it means to superpose 1 and 2 electrons, or 0 and 1 electrons. And so I think your point is extremely important.
Okay.
And when and when you have incidentally the second electron, you have to now treat it in exactly the same way as the first electron. You have to engage the temporal modes again and compute all of this. But I think the effect will remain in this case.
Cool. And have you written about this? Or
no, not yet. Actually, I've been sitting on this. I think Chiara and I have been sitting on this paper for about 6 months or so. I think it should be out very soon. I think it's briefly mentioned in this paper on arXiv, but I think I can send you a draft of this as soon as we have something reasonable.
Yeah, I'll be looking forward to reading that. Thanks. And then we have Lin Chin, who's asking a question as well.
Hi, I have a very simple clarification question. So the ghost field in your title has nothing to do with the Vedral-Popov ghost.
No, you're right. Actually, I'm kind of misusing the language. I like that Carlos suggested ghost busters, you know, the people who kind of want to bust these ideas. You're right. I think they have nothing to do with Vedral-Popov ghosts. These are actually extra things that you have to add, even on top of these guys. So I just call them ghosts because somehow they're frequently treated as unphysical, in no need of quantization, or whichever way you want to put it. But I think the ghosts you are referring to are even extra ghosts that you have to introduce. And I think they become extremely important, not so much in the electrodynamics, but if you go into the non-abelian gauges, then I think they become effectively indispensable. And I think it's a good point, because what is the meaning of these ghosts? And you can ask maybe similar questions. Could you talk about the reality of Vedral-Popov ghosts as well? It's a very good point.
Thanks.
Anjan?
Hi, Vlatko.
Hi.
Very interesting talk. I just wanted to ask you here at the end a little bit of maybe question stemming from my own confusion about something, but I like very much your kind of, so to say, down-to-earth quantum informational perspective on viewing interactions. So I was wondering if there is a way to describe in a concise way how you understand precisely this fake entanglement or false decoherence in relation to causality in a sort of more standard, let's say, quantum information sense, in the sense that the fact that you bring together the electron to one point, you're somehow dragging back the field. But how does this come together with the possibility of actually influencing another electron out there? So how should I understand this in a quantum information language?
Oh, I see what you mean. You are asking, if I understand correctly, you are asking how to connect the it's a good point, because in one case, you're talking about two charges now, for instance, and each of them has this kind of entanglement with the, let's say, with the scalar mode. So that's one picture that I was offering, how charges, let's say, repel each other or attract each other by effectively, you have to take them as really dressed entities now. So you have to think about this charge, not as the naked charge, as we know, but you have to treat them as dressed with these coherent states. And then jointly, when these two charges approach one another, effectively, really what happens is that the eigenstates of your joint system change. That's why I like this analogy with molecular bonding, if you like. So that's one picture. The other one you're asking is different in the following sense. If I make a single charge in a superposition, then because of linearity, there is no really cross-coupling between these two. All you have is just entanglement between the location of this single charge and the underlying field. So this, this doesn't generate any additional electrostatic repulsion, if you like. It simply gives you a reduction in visibility if you were to interfere this charge, like I said, but without closing the loop, in which case, you go back to this false decoherence. So they are clearly related because I'm using the same formalism, the same picture of coherent disturbances. But in one case, I think you have two charges, whereas in the other case, it's just interference of a single charge.
Okay, thank you.
Are there any other questions? Anybody would like to make a comment?
Yes, I have a question. Hello, am I audible?
We can hear you.
Yeah. Hi, Vlatko.
Hi.
My question is that when I looked at the form of your Hamiltonian, which basically showed the difference in the electrostatic energy of the charge configuration in two different locations, it seemed very reminiscent of what Penrose has talked about in his idea about spontaneous collapse. So there also he considers the the energy difference due to the different locations of a mass, right, which is placed in two different locations. So are there at all, is there any overlap, conceptual overlap or otherwise?
It's actually an excellent point, and it comes nicely after the previous question as well. I think that Penrose goes exactly into this other picture, which I was saying should not really be the case here, namely that he would say that even in a single mass that's superposed across two locations, this entanglement with the underlying field, which I agree would have to exist for the same reason as with the charge, he thinks that this would collapse superpositions. So my answer to that again would be that if you really do the interference in the way that you bring these two masses together, then this entanglement ought to be completely irrelevant. So at least in the linear regime, I'm talking about linear regime, I agree that when you include nonlinearities, there could be some extra effects, although I think they are far too small at the level that we are discussing now. But I think maybe some extra effects could then convert this fake decoherence, which is, I think, what you're suggesting, into real decoherence. I think that would be great to test. I do agree with you that it seems to me that's his intuition. That's what he's, I think, suggesting. But again, my bets would be that this would come out the same way as quantum electrodynamics. And there wouldn't be any fundamental difference necessarily at this level. But of course, I could be completely wrong.
Okay, another question I have, if nobody else is in queue, that when we perform this Gupta-Bloiler quantization, so we have these this constraint, and we say that the physical state should be annihilated by this constraint, right?
Yes.
So now, one of the things, for instance, we have learned in loop quantum gravity, right, where we get this famous EPRL amplitude, and the way that comes about is the realization that we have these constraints, but they don't need to be applied strongly, in the sense that rather than saying that the states are annihilated by the constraint, one can say that the constraint is imposed weakly. That means the expectation value of that operator, that constraint operator, vanishes.
Yes.
So in the context of electromagnetism, like, have you encountered anybody who's thought about that, or worked
No,
out the
not really. I
consequences,
think,
maybe?
yes, I think there are reasons to exclude this average, although, as you say, that's actually a very natural thing to do, right? Because that's almost like taking some kind of classical limit even for these modes. Let's just take the expected value, and as long as it's satisfied, it's okay.
Right.
It seems to me that this would be that this would give you different results, clearly, but I haven't thought about linking this to what I have in mind. I think that's a very interesting suggestion. I think certainly I've seen it voiced by various people, but I can't tell you immediately whether this would really change anything in this story.
Right. Okay.
Yeah, I think it's a good point.
Okay, thank you.
Right. Are there any other questions? Well, in that case, let's join me in thanking Vlatko.
Thank you.
Thank you for the talk. And see you all in a couple of weeks. Next one is going to be on Wednesday because we couldn't find another time. All right. Thank you, Vlatko.
Thanks very much. Bye. Thank you.